Vuoriston tekniikan ja luonnontieteen määräämänä valvojana Kosken väitöstilaisuuden vastaväitteenä tässä tilaisuudessa. Natural Sciences, Tampere University, this public education law. From Faculty of Science. Jari Aalto University. The doctoral defense recorded by joining
Honorable Custos, honorable opponents, ladies and gentlemen. Let me paint a landscape of what this thesis is about, the surrounding thematic or the framework that has been studied. Surface engineering. Why do we need surface engineering? Well, surfaces are everywhere. They can be hot, cold, hard, soft, and we don't necessarily pay attention to it, but everything you can touch has a surface. We only notice it when it's missing. Some everyday examples of this could be painting a car or a house, or lining a football field with fake grass, for example. And coatings are surfaces that bond with the underlying material, separate from the parent material. They're used in various applications in the industry for wear and corrosion protection, for example, among others. They can be thin, which would be under 10 micrometers. For example, this tooltip insert could be coated with a thin coating. What I call thick coatings would be upwards of 10 micrometers up to 1000, so 1 millimeter. Not really thick, but still in the scale of our studies, that would be thick. And above that, I would like to call these clads, because you can clearly tell two different layers of materials separate. What is thermal spraying then? Thermal spraying is a method of manufacturing thick coatings, so between 10 and 1000 micrometers. They can be virtually from any material group, so metals, hard metals, coating, ceramics, or polymers. And to make those, we need heat to melt a material that can be in the form of powder, wire, cord, rod, or more recently liquid suspensions or solutions. And once we have this molten material, we need to propel it towards a surface which we want to coat. And after this, the molten material hits the surface and makes a coating such as this one. The gray part here would be the coating, ceramic in this case, and a metal substrate. These coatings are used in, for example, in batch production, such as this ball valve for process industry that's being coated with a hard metal coating. We coat one ball and we stop the process, switch it up, and resume with the next one. It can also be used in continuous production lines, such as this coating of a stainless steel welded tube, where the weld area is void of corrosion protection, and we need to apply a new zinc layer on top of this to re-galvanize the galvanized metal. And it can be used in laboratory scale. Like in this case, there is a coating for my study being made. So even really small pieces downstairs here at the university. Some common applications of thermal spray coatings are, for example, possibly the biggest market is in aerospace, in turbines as ceramic coatings against heat to prevent the metal from melting or heating excessively. And in the landing gears of airplanes to replace hard chrome that is nowadays a toxic material to use. It's also used against corrosion quite widely in various industries. Metal coatings, shipbuilding is one big area where we use corrosion protection coatings. And it can be used in process industry also against wear or corrosion or both, such as paper machine rolls or in energy production boiler tubes. Now, thermal spraying itself is a value-adding technology, meaning that in most cases, the components would work without a coating quite well, probably a bit shorter time, but they would work. And by applying a coating, we can increase the lifetime of the component, maybe 5 times, maybe 10 times, maybe 2 times. And in some cases, it's not worth it to apply a coating. But thermal spraying by itself usually can be replaced if there is a better option from, for example, thinner coatings in thin film technologies such as chemical vapor deposition or physical vapor deposition, or thicker coatings, clads from laser cladding PTA or welding. So it is really a niche technology between thin coatings and thick coatings, and its use is quite niche as well. And typically, the technology develops from industry pull. There is some current need of a current component that could be made even better with a coating. It's not so often we see this type of research from the bottom up, starting from scratch to build some new application. But that happens as well sometimes. Then what are oxides? It's a compound of oxygen, O2 or O in a compound, and another element or multiple. And what we thermal spray are compounds of metal and oxygen, such as which are ceramics. It's a fancier way of saying oxides. Usually we talk of ceramic coatings, but they're most often oxide coatings. And the most often used are aluminum oxide or alumina, chromium oxide or chromia, titanium oxide or titania in my study. Possibly the most used is zirconium oxide, but any oxide pretty much could be sprayed. And it can come in almost all feedstock forms, not wire, because ceramics are difficult to make a wire from. Now, thermally sprayed oxide coatings, what are they? They are chemically stable for corrosion protection if they're dense. They resist sliding wear, also other types of wear, but really against sliding wear, they're really good. And they have good release properties where that's needed, low surface energy, and they're hard. What they are not is resistant against impacts. As many of us know, ceramics are very easy to crack. And that in the case of a functional coating, it often means that the whole component is out of use after this. So this would be the industry pull in my case. The damage tolerance would need to be increased, so less cracking of the components. And thermally sprayed oxide coatings have a ton of flaws. The process is stochastic. There's uncontrollable factors or difficult to control factors which lead to porosity, unmelted particles, cracks, etc. And it's very difficult to eliminate these totally. So most often we try to find the best balance and control them as well as we can. And to find the optimal properties, which means compromise. Some property goes up, some goes down. Most often we haven't found the perfect solution to make everything better. Now, damage tolerance itself, it's in the name, but in simple terms, it means how much damage can the coating endure before it's unusable anymore. And it's a combination of many things. It's not just wear, but there can be fatigue from thermal cycling, adhesion problems, corrosion. And in this study, for example, we've studied the cracking behavior up close, trying to quantify this phenomenon. Okay, so finally, the holy grail is damage tolerance. So how did we approach it? First, we need to figure out what coating characteristics are at play. How do they affect damage tolerance? And how do we measure if they do, which is a challenge by itself to measure this property. And there is about half of the thesis is about these topics. And once we know this answer, how do we improve it to make a better coating? And this is roughly half of the thesis dedicated to this topic. Thank you. I ask you, honored Professor Christopher Berndt and honored Professor Jari Koskinen, as the opponents appointed by the Faculty of Engineering and Natural Sciences of Tampere University, to present the observations and comments on my dissertation that you consider appropriate.
So, Mr. Chairman, shall I lead off? Okay. I have many comments concerning the thesis, but first of all, I'd like to comment on the presentation. The presentation was very clear, it was very concise, and it reflected very well the contents of this purple book. I did like the idea of giving a very high picture view of the various manuscripts that contributed to this thesis. When it comes to the questions, I'll be asking some questions later on. When it comes to the questions, these questions will be phrased from the point of view of helping me and others go into a little bit more detail concerning the science and the technology. to be an opponent, as an opponent should be, I would make the following observation. There needs to be a relationship between the microstructure and the testing technique. That is quite important. That connection was very clear within the presentation, but the processing, structure, properties, performance might have been a little bit more clear within the thesis. But this will be brought out, I am very confident, within the discussion period later on. So this critique is really focused towards the other students, the other candidates who'll be following you. That is a very broad picture view. Within my actual commentary, I talked about the general nature of the dissertation. I talked about the novelty, which I think was very novel, and how the thesis was put together to tell a very story. I looked very carefully at the data. I looked at replication of data. There are many manuscripts out there where there is no replication. I was pleased to see replication. That came within the clarity, and hence the mastery of the research methods became quite clear. I would consider this as positive critique. When it comes to the questions, though, we'll dive just a little bit deeper. And again, I emphasize this is to clarify certain things in my own mind, as well as to give instruction to the candidates who follow you, that they need to think very, very deeply. Then, just a closing down before I hand it back to my other opponent colleague, Jari. I believe that the quality of the thesis was more than satisfactory. The literature search and a survey was very good. And I'm smiling as I say this. I was pleased to see that some of my work was referenced. So that was a very so that was a very nice thing to do, even before you knew who the opponent was. So that was very well done. And this is another hint for those candidates who follow you. Be aware of your audience. I think that the maturity and critical thinking skills were displayed quite well. And writing in English is always difficult, even for native English speakers. And I thought that that was very well done, especially given the fact that you're able to publish. And again, to those people who follow you, those publications help writing theses, and it helps credibility with regards to your wonderful university, and it helps provide support to your advisors so that other candidates can follow you. So in summing up with regards to my critiques, I can hand this over to the other opponents. I was very pleased to read this thesis. I did read it. As you will see when I go through my notes later on, I did read it very closely, and I made many comments that will be revealed during our collegial discussion just in a little while. But what I'd like to do now is hand this over to someone else to continue this wonderful thesis defense. Thank you for this opportunity.
Okay, so I want to thank the opportunity as well, and I'm looking forward to a very interesting discussion here. I would think that first of all, to make communication easier, let's agree that we will use our first names in the discussions to cut the corners of the formalities. So that's perfectly okay with all of us. Yeah, let's start discussing about the very extensive thesis dissertation document. And my first question would be to Jarkko, that how did you come into this this theme? It's a very wide and you sort of like you want to solve in one thesis a very broad area of problems, both how to characterize them, how to understand them, and how to solve them. So how did you come to this topic?
Well, you hit it right in the head with commenting that it's a very wide topic in retrospect. I did want to solve this problem, and I wanted to not limit myself to one type of a phenomenon, such as fracture toughness right off the bat. For example, to go yeah, it's kept wide by purpose, but also by chance, because as I was going through it, it seemed there was more aspects to go through.
Mm-hmm. I would understand that typically when you, as a PhD student, you start research, you have a nice idea to solve a problem, or you have a nice concept how to understand a phenomenon and describe it. And so you must have had some key ideas to start with, and then you find out that maybe it's not always so easy.
Exactly.
So let me actually pick up on that, if I may. One of your key ideas, Jarkko, seems to be toughening and strain tolerance, looking at stresses, and I'm referring to the introductory pages of your thesis, pages 23 to 25. There is a lot of discussion and a lot of thoughts about toughening. So this is another holy grail with regards to this technology.
Yeah.
And I don't completely understand strain tolerance. So could you please just explain to me, or actually to the world who is tuning in, can you please explain what you mean by strain tolerance for thermal spray coatings? And it'd be interesting to get your thoughts about how strain tolerance can be controlled. Would you be able to just expand a little bit on that, please? Is my question making sense?
Yeah.
Well, first of all, it's not a question. This is just an inquiry, right?
Yeah. Strain tolerance, I see it as, well, for example, this coated component, you would pull it apart, the substrate deform elastically, and the ceramic coating at some point, it couldn't take this strain anymore, but it would have signs of cracking. So this would be, if it's 1% of strain or 0.5%, 0.3, to me, the first sign of cracking would be the limit for this coating. And that is my idea of strain tolerance in this thesis.
So let me just dig a little bit deeper. This is a question that I ask myself every time with regards to ceramic coatings. Are cracks good or bad? Is porosity good or bad? Is there a mix of these voids which may actually increase strain tolerance? Well, what are your thoughts about that? And then I'll hand it back to Jari.
Okay, that was a good question or comment. Well, as I mentioned in my lecture, there's industry pull for developments often, and in my case, we wanted to have also dense wear-resistant coatings with higher strain tolerance. So in our case, cracks and voids generally would be deleterious, so unwanted. And later during the thesis, I did discover that they are actually beneficial for strain tolerance in the sense that they're pre-existing cracks. So to make a new crack, you would first open the old ones, so that would give a bit of a leeway to strain. And this, for example, in thermal cycling applications would be beneficial. There's no additional cracks coming, it's just old ones opening and closing. Did that answer your inquiry?
Well, I don't want to hog the floor here. I think that let's give our colleague Jari a chance.
Okay. I look at when we advance from this background, we come to the aim of the work. I think it's well defined, twofold. There's like two frontiers. One is the understanding and characterization of damage tolerance, crack propagation resistance, impact resistance, and second goal is how to improve them. So how to understand how to improve. It's a lot of things, and it's divided into research questions, and the answers could be found in publications as in table 1.1. If we come to the very introduction of the thermal spray, I think we always see this figure 2.1. It's like this is thermal spray. This is the splats forming the coating. Then you show that one image is 2.2. It's an image of a copper metal splat. Can you explain how that describes the process that we are dealing with ceramic coatings, this being metal, and how would it be very different?
Yes. In my mind, it's the phenomenon would be the same for molten ceramics, and I was wanting to find the best picture to describe this splattering during spraying. So in this case, it was molten copper instead of molten oxide. But as I see, compared to the coldish substrate, the phenomenon would be the same. The temperature difference is high in any case. If you agree, I don't know.
Well, yeah, I guess the phenomena are similar. If I still go deeper, if it's not ceramic, then in the following picture, 2.3, again, the dynamics of the splat formation. How would you use this type of image and take into account let's say the important ingredient in development of these coatings in this thesis is the nanomaterials. How would the nanoparticles show in this type of an image?
they would still, I think it would be the same image, but in a smaller scale. Of course, if they're very molten, they probably wouldn't stay nano. They would be there would be crystal growth in this case. So maybe a splat so flat would need to be very molten and not nano anymore. But that's a tricky one.
So if I could just chime in here just for a little while. These are the classical figures that we always see. And the things that I'm just wondering whether Jarkko could describe a little bit more about surface roughness effects with regards to splatting phenomena. What happens when you get to second, third, fourth, fifth, sixth layers? Whether the modelling, which a lot of people do, is of interest. I'm just wondering whether Jarkko, whether you could help the audience and me understand just a little bit more how roughness actually and other practical aspects influence these wonderful cartoons that we always see. Jarkko?
Okay, I will get a chance to use the blackboard. If you so the roughness magnified of a surface would be something of this sort, and we measure the roughness based on the peaks and valleys. If the splat is too big or the roughness is too small, the splat would basically end up staying on top, and the consequent splats would come on top of here to form the coating. But this is not a good adhesion for the coating, and it's also not good heat conduction to the substrate. So there's these two factors. Another option would be if the splats are the right size, say according to the surface roughness, when they approach, they would deform on the roughness, but correctly. Next layer would come on top of these, and the roughness would be somewhat replicated, but it would be removed layer by layer until we get a good coating. And what's missing would be if we sprayed, say, nanoparticles for too high a roughness, then we would get them inside all over, pretty much copying the surface roughness of the bottom of the substrate. And I think in this case, now it's hard to make sense of it, but I've seen it to make pretty much copy the roughness, and the surface roughness of the coating would be high as well. In these two cases, I'd say adhesion is better, as is the heat conduction to the substrate compared to too big splats or too small roughness.
So the second part of the discussion concerned modelling, thermophysical modelling, and well, can we believe it?
In the case of thermal spraying.
Yeah.
It's.
I better be careful what I say here because some of our friends are on the call here.
There is some so personally, I find it challenging. There's many variables to control in the process, and after all this, within each splat here or in the picture, you have local differences in phase content in phases. Maybe there is some precipitation of different materials. So to account for all this, you would probably have to go backwards from experimental results, a lot of them, make a model, backtest it, make a new one, backtest that, and still to transfer this model that you did in your laboratory and say it works universally outside of your laboratory is challenging. It's not unimaginable, but there is work to be done.
Yeah, if I want to continue a little bit with this same theme, in the thesis there's described all these different thermal spray methods and their advances and characteristics. Then there comes this chapter 231 on properties, mechanical properties. There is this. It's not a table, but it's this one that you show the different features. So I think these are related. What are the processes related to the splat formation that actually affect not only the cooling or spreading of the molten or semi-molten particle? Can you describe?
You are talking of this stress generation, residual stresses?
Yes. Yeah.
Yeah, well, there is, of course, the thermal effect from the quenching, as is the first part. And, well, the splat will have some property as it first arrives, and it will be, of course, altered by the consequent splats that come after that. In this case, it's peening stress. Like mentioned here with ceramics, it's not seen as such a big effect because they are already quite solid and hard. They wouldn't deform so much as to crack, so potentially they could crack from the incoming particles. And finally, the thermal contraction comes from the difference in thermal expansion of the substrate and the coating. Did I miss the question, or you look puzzled?
Well, I think those are the issues. I was thinking, like you said, that do I recall right that there have been some experiments in adding some peening particles there in purpose to densify the splats during the deposition? Would that be beneficial to close the cracks or something?
As far as I recall, these are with metallic coatings that you would add ceramic particles maybe to add the stresses and also improve the adhesion and cohesion.
Yeah, you're right. It might not do much effect for the ceramic. But then can you describe the differences in the coatings? I think it's quite critical. Some of these coatings have tensile, or most of them are in tensile stress, but some of them are in compressive stress, which is, let's say, a big difference in the mechanical properties. Can you elucidate that in different materials for using this figure that you showed?
Yeah. Well, ceramic coatings generally would be in tension because of the lack of peening stresses. Plasma sprayed coatings almost always, I want to say. The compressive ones that I did find were HVOF sprayed coatings, and in these, I think HVOF spraying of ceramics requires a lot of heat, gas flow, and we heat the substrate so much that it expands. So after it cools down, it compresses the coating. It's not from peening. I think it's more from this cycling.
So the thermal load in HVOF is higher to the substrate.
Yes.
Okay.
It's a lower temperature than a plasma, but there's so much gas going that the heat transferred is higher.
But with the chromium oxide, you tend to get this compressive stress.
Especially because it has a high melting point and we need to crank it all up with the HVOF as almost as much gas as hot as we can and hope it sticks. So it heats the substrate a lot more than other alumina or titania that we try.
I see. Okay. Yes.
So your thesis, Jarkko, has an industrial application, many industrial applications. Mm-hmm. So when we look at residual stresses, as you're showing there in figure 2.7, I'm just wondering whether you could explain to the industrial people on the call here that when you spray an ID to an OD or an OD, the outside diameter or the inside diameter of, say, a tube or a curved surface, then these residual stresses can be good and sometimes they can be bad. Can you just clarify to, this is a question I think that we all get many times about the practical aspects of thermal spray. Could you just talk a little bit and just imagine I'm an industrialist and explain to me that sometimes, or to us, that sometimes residual stresses are good.
Yeah. Well, residual stresses usually, especially in our applications, are beneficial in the compressive side or wear-resistant coatings. I don't know, does it increase hardness, but wear resistance for sure. And it's not so easy to create a crack by tension when there is compressive stresses keeping it apart, keeping it intact. For the tensile side, I'm not sure I can't identify an immediately beneficial use, but it's not necessarily a bad thing if the process afterwards where it's used is controlled.
If you wanted to get a near net shape and have the coating actually fall off, and people do that. So this is in other words, there are instances where crack propagation or relief of the coating from the job to get a near net shape, which is then post-processed, might be an attribute. But I think we'd all agree that, sometimes we highly want compressive stresses.
Okay, please.
There was one question that you mentioned during your presentation about ceramics not being able to be formed into wires. I'm just wondering whether you could talk a little bit about cord wires and maybe even bring up the Oxide process where we use ceramic rods.
Yeah. Well, in that sentence, I thought of wires as being deformable wires, like a metal wire. Cord wire, and that can't be done by ceramics.
Yep.
Cord wires, you mean metal wires that have ceramic?
Yes.
Yeah. So these would have ceramic powder inside the metal, and once it's just a way to transfer the ceramic into the flame, similarly to the flexible cords, the flexi cords that have, instead of the metal, there is an organic skin around it, just to get it to the flame, and after that, the main part is the ceramic inside. And
thank you for your very clear clarification. and I guess I was being very pedantic in my comment, but thank you for making sure that we all understood that ceramics can be sprayed in a variety of forms to form these wonderful coatings. Sorry to interrupt so much, Jari. I'll give the floor back to you.
We have 24 hours. Thanks. Yes, we proceed here. It's touching the different materials, ceramic materials, in very nice compact way. What interested me is this functional property of this zirconia stabilized material, where you have this crack arresting behavior. That sounds nice. To arrest the cracks. It's on page 43, I think.
Yes.
Can you tell more about that? You conclude here that, however, the usefulness of the crack arresting behavior is dubious in thermal sprayed coatings. So is there something to look for, or is it doomed to be not important ever?
There's something to look forward to if we could create dense enough coatings, possibly. But for now, as I mentioned in the lecture, there's pores and cracks and voids, discontinuities inside the coating that make they have a larger effect. So this crack arresting I can't see, and I've tested it with some various methods. I didn't find an effect of this, and probably it's because the crack won't be arrested here if it has a pre-cracked route to go around, or a pore to enter, or the lowest resistance of propagation. So in bulk materials, this is used, like in this figure 2.9.
Yeah.
But in a coating, you can find this ideal box of tetragonal zirconia particles.
So if you would have an intergranular crack, you might have something like that, but when it's not, then you would have anything.
Yeah, I would imagine the crack even going at the intersplat, between the splats, rather than entering the splat and causing this. Yeah. Unless the cohesion is high enough, but for now we haven't gone there.
Yeah, I understand that is one of the strategies in your work, that to get the splat adhesion better within nanoparticles. We come to that, I guess, later. Yes, I would be willing to go to the next chapter, damage tolerance in thermally sprayed ceramics, unless, Chris, you want to. No. Can I just start here? When we look at this figure 3.1, and it says performance and processing considerations in producing damage tolerant coatings. How is it, let's say, really specific to damage tolerance? To me, this looks like how to create and develop a thermally sprayed coating.
Yeah, that's a good point. Unless you would want the coating to be, if you're not looking for mechanical strength, such as thermal barrier coatings, then you might not care so much of the cracks that would be there, or the damaging. You still care of erosion resistance, but this is it is quite wide. I agree on that, but it's especially for our kind of use, against damage tolerance would be the recipe, the golden road.
Okay, yeah, thanks.
So when we talk about damage tolerant coatings, there are though instances where defects in structures are desirable.
Mhm.
And there are industrial examples in wonderful thermal spray technology where defects can be controlled. So damage tolerance has a very interesting meaning. So I'm just wondering, Jarkko, whether you could think of some immediate applications or even some future applications where crack networks or porosity networks or something which is being described as being damaged now is actually good.
Well, application-wise, I'm not sure right now, but based on some studies I read from CNRC from Canada, I think, they had sprayed with HVOF titania agglomerated sintered particles that had primary particles were nanosized, and there was some unmolten particles in the coating that then acted as crack arresters, because from the cohesive part, the dense part of the coating, you get a crack propagating, but it comes to this, that's essentially, it's a discontinuity like a pore would be, but maybe not so undesired. And this nanostructure then stopped the crack. And I could imagine titania coatings like that could be interesting in sliding wear applications, anywhere where a titania coating would be used, but these would just be better.
So let me just dig a little bit deeper. Do you think, I don't know the answer to this, by the way, so this is not a trick question. We're just speaking as colleagues. Do you think that the crack network could be used as a membrane filter to filter out something, either filter out a gas of a certain large size or to filter out some noxious virus? There we go. Do you think there could be, what do you think? I mean, and there's not a right or a wrong answer here, or this is just a discussion. Mm-hmm. So what do you think about that, Jarkko?
Yes, why not? We've tested already with our HVOF coatings the gas permeability, and there is small gases that go through, larger ones that don't. Then if you would find the parameters to tweak in the spray process or the feedstock to somehow control the crack network, to have the crack size proper. If you want to filter out viruses, you want to be sure there's not one crack that is just a bit too big, or one crack path through the coating. And but I can see this being of interest, like what we achieved with our HVOF coatings, a bit more throughput of larger gases.
So I'll hand this back to Jari just in a little while, but in the pure sense of your thesis, the phrase damage tolerant, I'm just wondering that would kind of be incorrect, wouldn't it? If we had an application where damage is a bad word. Mm-hmm. Would you agree with that kind of statement?
I would.
Okay. I'll hand the chair back to Jari.
Okay, thank you. I want to go a little bit further, not very much, but so is in fact this figure 3.4 something that you're discussing as nanostructures stopping the crack growth?
There you go.
To me, it looks like some unfortunate damage. If it is an indentation spot, it's really difficult to see anything, but maybe so. Yeah.
Yeah, this is exactly that, actually, from this publication that I remembered the topic probably.
Okay. So it doesn't replicate the tip shape by any means. It's just a crack, but maybe it's minute compared to the expected or something.
Yeah, of course we can see what's outside of this 1 micrometer image.
Okay, we come to the next subject, chapter, nanostructured coatings from liquid feedstocks. Do you have evidence of really so all these ceramic nanoparticles would be melted in a process? Wouldn't they? Yeah, if they are isolated, they would be melted. Maybe some evaporation might take place if they are really small. How do they survive this molten and flight and all that? Can you describe some of that? What happens to the nanoparticles when you melt them and put them into the process?
Yeah. Well, yes. If they're large agglomerates of nanoparticles that melt much, they start to melt, the particles would start to melt from the surface. And probably there we wouldn't have a nanostructure soon after. But inside the particle, so actually often when we find nanoparticles in a coating, it is unmolten particles that are embedded in the molten matrix of coating. And in these cases, for example, in solution precursor spraying, when the nanoparticles are formed in situ, in the flame or in the plasma, then I think they are reasonably isolated. And for the ones that are not, they have less time to melt.
Yes, I guess it's really an academic question. It would be very difficult to actually characterize that and see what happens. But I would basically repeat the previous question that I had at the quite beginning. Do you have have you ever seen images of nanosplats?
No.
Yeah. Are there any?
I suppose not. And it would be because the coating, like I mentioned, most often our nanostructures are still a mixture. It's a multimodal kind of structure. There's nano areas, there is micron-sized areas. So if I look at the coating from the surface, you could maybe see some small nanoparticles here and there on top of the coating. That's what it would look like from the top, in my opinion.
Yeah, I would imagine it's quite difficult. I refer to this image 3.5 and 3.6. In 3.5, you mentioned in the SHOF, HVOF that we see small grains. Would these be something to do with the nanoparticles in the process, or what? And the similar, I think it's claimed in the following picture 3.6 that or do we see some nano phases there? Taking into account this very low magnification, could we see anything?
Not really. I think in the right one of figure 3.6, there is the nano HVOF that has a lower temperature than the plasma spray coating on the left side. You could see these clusters, white clusters, that would be the zirconia, quite poorly embedded. It looks just like the coatings from one of my publications, where there are actually almost discontinuities of unmolten or poorly molten zirconia clusters. And inside that, you would probably find nanoparticles if you would zoom in. But then the benefit of these particles in this form is a bit question.
Yeah, I agree. I think you have in your publication similar images. So some of the nanomaterials actually make an agglomerate and they fly along with the particles, and they land as an agglomerate and most likely have the nanostructures within. I may still continue a little bit. Still under this image 3.6, there is this fracture toughness increase. There are significant numbers related to nano and this improvement with different nano materials included. So there's really an increase in toughness values. So it seems like a very attractive field, nevertheless.
It would seem like that, but to me, as you noticed, I didn't have fracture toughness measurements in my thesis, and especially when it comes to these nano coatings, I would somewhat challenge the transferability of these values, because you measure crack length, and as we saw, the crack can stop in a cluster like this.
Yeah.
And then you get a high fracture toughness, but it doesn't mean that it has a higher wear resistance or it couldn't damage afterwards. So it's a artifact of the measurement method in these cases, I think, since it's so characteristic, but then you look at the pictures and it's not necessarily a cohesive coating.
Okay, thank you.
Shall we move on?
Yep, please.
So I'm just wondering whether we can move on to the next chapter on page 57. I'm saving all of my questions for this chapter. So, well, as you're probably aware, I have a great interest in measuring properties, so I did focus quite a bit on the determination of these features. The area with regards to acoustic emission I found interesting. So let's go straight to figure 4.2. When we're talking about impact resistance. And, oh boy, this is so interesting because there is so much information. So what I'd like to start off with, Jarkko, is give, looking at this figure maybe, or other figures, or even the blackboard, I'd like you to define and describe micro versus macro cracking so that we're on the same page. How do we describe micro and macro cracking, and how does this lead us to vertical to delamination cracks? And how does this lead us towards adhesive and cohesive failures? So that there's a lovely story with regards to this figure 4.2. So maybe if I can just help you while you're thinking about this, maybe I can just guide you a little bit. Can you start off at 0, 0 and describe to the audience what is happening with regards to cracking, with regards to those regions that you've identified as 1, 2, and 3 in Roman numerals, and then how that's related to the AE, acoustic emission responses, that start off at a deflection of about 5 point whatever millimeters. Have I given you enough time to think about a response
Yes.
so that we're on the same page, or do you want me to talk just for a little bit longer?
For a few hours? No, I think I can try.
Thank you. Thank you.
Okay. Allow me some time to draw a coding.
Yep. So as you're drawing the coating, let me just talk a little bit more, and you can hopefully multiple process as you're drawing the coating. What I'm seeing here, or the interesting thing is, I see that the onset of cracking is occurring. Now, of course, this is a bending test, but I see the onset of cracking occurring in region 2, which is presumably analogous to pop-in if we were talking about fracture mechanics, or we'll be talking about plastic deformation. That's not entirely correct because it's a bend test, but I can see that there's a nice correspondence with regards to cracking mechanisms. How are you going with your drawing?
Finished.
Good, well done.
Now I can start explaining.
Thank you.
So at 0.0, coding would look like this. You would start to bend it, which is a tensile stress.
Yeah.
From this side, in this case. And once you make to the onset of cracking, as recorded by the AE, would be micro cracks. In my thinking, that would be individual splats cracking, perhaps some delamination between the coating. So these would occur continuously as long as we keep pulling the coating apart, essentially. Afterwards, the macro crack, I would think, is once these join and you have a true crack that you could actually see, probably not really, but you could easily hear it when bending. So these would probably be midway from the onset of cracking to the finish line. And so you would start to have more and more of these. And at some point, these would start to also, once the crack comes here, it either stops, but it can also start to, if here cohesion is higher than the adhesion, then the crack could start to propagate between the substrate and the coating. And finally, what you see from the after Roman numeral 2, before 3, at the end point, you have actually pulled it apart, the substrate and the coating, so that there's some open cracks. And there's deformation, plastic deformation of the metal substrate. And when you let go, it doesn't, the substrate doesn't go all the way. it stays a bit higher, the amount of plastic deformation, which would be the deflection of 8 millimeters. I guess it's measured from, I don't know where,
Yeah.
or it's a big piece. But in any case, it would stay here. Some cracks would also stay open because of that.
Okay, I'll just have one follow-up question before I hand it back to Jari. Go back to figure 4.1.
Yes.
Now, I'd like you to reverse the coating so that the coating is in compression.
Well.
Now, with regards to the science, well, by the way, I don't know the answer, right? This is not a trick question. But I think it'd be an extremely interesting scientific question because it might tell us how these cracks that you have just postulated can be validated. Can you just, in other words, if we were to turn the coating around now, how do you think the acoustic emission response would be? Do you think it would start off at 0, 0, for example? So go back to figure 4.2 and see and postulate, you know, that you've already done your thesis, so don't worry about it. I'm not asking for further experiments. I'm asking for, I'm trying to work this out myself, and I'm just wondering whether you can help us as colleagues work this out. Do you think that the AE would start at 0, 0, for example? And Jari, please chime in if you'd like to help Jarkko and I work this out.
Well, well, first of all, this 4.2, I didn't check right now, but it seems like it's not a ceramic coating since the cracking starts quite late.
Okay.
But thinking of a ceramic coating in compression, I'll draw again. It's good practice.
Yeah.
So I would have this same, I'll make it a bit simpler, the coating now. Make it a cake. And you start compressing, which would essentially be the bending test in burst. So you would have this ceramic here in compression. So you'd probably, this part would bend for sure since it's metal. This part would want to bend, but it might resist a bit. So we would see delamination here. And afterwards, probably some V cracks as you have a crack coming and the coating gives in. But as to when it starts, I think it would be really, hopefully before tension. In that case, it would be more damage tolerant in tension, I guess. But it's interesting.
Yeah, I think it's a good question because a lot of your experiments, in fact, produce compressive test spread states. Well, they are mixed of everything, all of them, but nevertheless, it's compression in a lot of cases. So it's a good point. Well, before we must remember that now at this stage we are still in the methods part. We haven't gone to the results yet, which is so maybe we need to speed up a little bit. But I cannot resist commenting on this figure 4.4. When I looked at this paper that this is originating from, it was an interesting conclusion, this paper from 1995. Do you remember anything, Jarkko, on this?
Vaguely.
Yeah, it basically says that the this erosion process is still a mystery. It was a mystery 50 years ago and still is. That's like a conclusion of this paper.
Depending on the particle and their angle,
Yeah,
you get different
in
results.
all areas of abrasive jet wear mentioned here, there are still considerable contradictions and gaps in our knowledge, considering the importance of abrasive jet wear. Elimination of these contradictions and gaps would seem to offer a rewarding problem for materials development. So it's like it's very strong opinion to make that type of conclusion of paper. You have to have a good name to get it published. Okay, but that's back already 25 years ago. How about going to materials and methods closer to what was actually done? I have one question. Basically, you have carried out a large set of experiments varying this and that parameter, but I don't recall seeing ever a statistical experimental design used. Wouldn't that cut some corners to find some interesting parameters, like in paper 5, you vary number of parameters. Did that occur ever?
Yes, and indeed, I like paper 5 because we did quite a thorough search, not a design of experiments by any means, but more of a still spending time. And I guess many of the publications and the thesis itself is a picture of the times. It's different interests that evolved during the thesis, and at some point there was a high interest to test many materials and to do such an optimization to all of them. Unfortunately, in thermal spraying, there's so many parameters and outputs. You first need to define your output, make sure it's good. Then you need to define the parameters to change for each material. So yeah, we didn't do it. If I had funding for 5 years to study this topic again, I would choose less materials and go more thoroughly through them.
Okay.
So when you look at table 5.1,
Yes.
is it correct to say that you only used off-the-shelf available commercial materials?
Not exclusively. For fused and crushed materials, powders, yes. For agglomerated and sintered, we did some collaboration with Millidyne, for example, Chromia 5 Titania. I can't say on their behalf, is it a commercially available? Has there something been changed? Is it a development project on their end too? And then suspension was commercial at that point already, and the hybrid spraying was the constituents were commercial, but we mixed it ourselves.
So I guess my real question is, not question, my real comment or inquiry point is, do you think that there are other opportunities, and maybe you've already answered this previously, but it's worth repeating to the younger people. Mm-hmm. Do you think there are opportunities for other materials, other powders, other than those that you've got listed to form damage-tolerant coatings?
Absolutely.
Okay.
For sure. We didn't come to this particular brand of powder size for damage tolerance. We came from past experience and yeah, it was a choice of convention in many cases.
Well, if I remember, I'll ask you that question again in future work.
Yeah.
If I remember to answer that question, but for the time being, I'll hand it back to Jari.
Okay, thanks. About these characterization methods, I think I find this exotic and interesting, this high velocity particle impactor. To me, it looks like it's like simulating the catastrophe. Yeah, don't do this in your manufacturing facility type approach. Yeah. So I think what you actually do, you shoot it with a heavy bullet, the surface, and basically you know that it will be killed. Would it be, is this a type of a experiment where you would not be able to, let's say, gradually increase the speed of the bullet and change the location, and then afterwards look where did you actually do and what? Now it seems like you are looking at the dead body and try to figure out what happened.
There was a high-speed camera involved that gave beautiful videos of ceramics shattering. Mm-hmm. But that was, at that point, that was the characterization, but it wasn't really live. It also had to be processed after. A load sensor could be interesting in this one as well. But as it was now, it was more of a, we could change the velocity and the size of the bullet, as you said it, and see what remains.
So it takes a long time to reload that. It's not a machine gun. It's once in an hour.
Yeah, it fills this chamber with pressured air, and then you hide behind the corner and press a button, and it releases all the air at once, shoots the bullet, then you change the sample, repeat. It's
like the Middle Ages gun.
Pretty much. And the barrel was actually a rifle barrel, I think so.
Yeah, but they are ball bearings that you shoot, I guess.
Yeah. Yes.
Okay, but I guess it's a well-instrumented experiment. No question. You have these cameras. So is it true that you can actually measure the loss of energy to your surface from the collision, the inelastic part?
Indirectly. So that was with the high-speed camera. Yeah. We could measure the velocity before and after, and postulate that what's the difference is the difference in kinetic energy that has gone into the coating substrate system. We couldn't measure the energy, but we used some theory for it.
Yeah. Yeah, nothing more on that. That's an interesting experiment. You could be used a lot, but it's tedious. Yeah.
Yeah.
So I have some comments, and hopefully these can be some brief comments about why 4-point bending and why 3-point bending.
Mm-hmm. Why did I use both?
Yes.
Well, initially, I wanted to use 4-point bending in the macro test because it gives a larger, it's a larger area of coding that is under tensile stress. If you use the 3-point bending, you presumably create the crack right in the middle. In the in situ SEM version, wait, I will just get for the audience some sort of picture. So here's the 4-point bending, no picture of the 3. But in the 3-point bending inside the SEM, if we used 4 points there, we might get cracking where we were not looking, because we're looking at a reasonably small area of the coding.
Thank you.
And the micro impact fatigue, it seems to be the champion in some of the best results that you obtain here. Just a little technical question. Did you, well, okay, one thing that wonders, why do we have such weird parameter as what was it, the activation time or something, instead of load or velocity or energy of impact? Wouldn't there be a direct correlation?
There would, yes, but I wanted to use the input. Well, the impacting sphere, or this rod, was accelerated by electromagnets, and we could change how long we accelerate it for, and the rest it goes by its own weight. So this was our input. Then we measured the velocity with an optical sensor of the impacting phase, but it's not always exactly linear. The increase in acceleration time, or even keeping the same one, you would get small variation with the velocity. And I think it has also something to do with measuring of the velocity. So also to make my tables that are later on somewhat sensible, it was nicer to use 0.7, 0.8, 0.9 that were the same for all codings in the same column, instead of putting the individual velocities and energies that I did calculate those two and tried, but then it would have been a mess to understand. Okay, yeah, maybe there's some development potential in this device still further. About the measurement, do you monitor the sphere, the condition of the sphere? I did once. I took a sample of the sphere under a microscope to look at it, but not more than that. I was just curious, is there sticking? But we did change the sphere between each sample. Or we rotated it until there was no phases, and then we switched it. So it's not the same one going from coding to coding. You might have mentioned that in the publication, but I don't recall. That's why I asked. Okay. Right. How about going to the results and discussion? Or Chris, do you have anything?
I just want to ask a curious question. This may be completely out of scope. This chapter is very nicely written. And as you read it, it seems, oh, this is so easy. This is so simple to do all of these experiments. But real life is quite different. With regards to, and again, this is for other people who may be thinking about following the same track. In your experience, Jarkko, how long does it take to get a result from, say, a 4-point Berndt test, which is a good result, which is a rigorous result? If you have the test method ready and validated, it would probably take, for one coding sample, 2 days or so. Afterwards, analysis, maybe 3 to 4. Okay. But there's a big if there. Yeah, it all depends. You want to have, first you want to bend just the substrates many enough to have confidence in their acoustic emission. Then you bend many codings to get to the variation. Good. That's what I was getting to, is that there are many other experiments before the experiment. Yes, for sure. And these test methods have been changed a few times, improved once we did all the tests and saw there was something wrong. We changed it, had to do it again. So all these took months. Thank you. I think my colleague wants to move on to page 73, results and discussion.
Yeah, something like that. Very good. So it starts with this impact resistance experimenting. So you have two approaches used. One is that you hammer the surface 1,000 times, but you have a different impact energy in each. It's test impact, and then you look at the outcome. Or actually, yeah. So you let it hammer 1,000 times, and then you see what happened. That's the first process. Was that also the first process to start with?
There was a few experiments before, but not many. Thing was, I traveled to France for 5 weeks with a limited amount of samples. So we tested a few samples to find some parameter idea. They hadn't tested thermal spray coatings as such before. So we had to find some window where to operate, make good guesses, what are the parameters that we want to try. And yeah, after that, there was not very much optimization.
So do you mean that, I'm not so sure, but tell what type of literature is there on this similar types of experiments? Is this a frequently used method, even though not used with this French device?
To thermal spray coatings, I haven't seen many publications. I know the existence of a handful of machines, maybe 3, all different. It's not the same design. I don't even know what the others look like. So I presume they have been used in some projects, maybe industry projects, but publications I didn't find at that time anyways.
So if I may continue, then the second approach is to to select a load. I wonder how was that selected? This is maybe deduced out of the it seems to be close to the maximum excitation time that you use for the increasing time of impact. So you make 100, you look at it, you continue. No, I guess you make 200. You don't try to aim at the same place, but it's but then you get an advance of what's happening.
Yeah, it actually, the testing itself was really fast. Well, I chose the excitation time based on, and that was the tough part, determining when has this coating failed. When I changed the excitation times with a constant load, constant impact repetitions. Yeah, number the 1,000. And I looked at the micrographs. I was there on site, so I hadn't done the analysis yet. And I looked where did it break, and choose this as the excitation time and try to find the point where it doesn't break. Can it take 100 repetitions or 2 or 3 or 4? But the test itself is really fast. I could program it to do like 100 and then move 5 millimeters to 200 repetitions. So I did these all, and then I went to look at them in microscope.
Yeah, I think it's very elegant way of determining when you measure the cavity dimensions.
Mm-hmm.
Then you figure out at what stage the increase takes on. So the speed of erosion is highest, and that's the critical point, and that's you say that's the required impact energy for failure. Did I understand right? Because it's like that criteria for this 6.3.
Yes, there it was basically the number of repetitions times the energy of one impact would be the required impact energy.
Okay.
That was the attempt to quantify this quite artistic approach.
No, I think it's very elegant. So you have a quantitative, let's say, measurement where you can say that this much energy is required for the failure, as deduced from the sensing.
Otherwise, it would be a bit difficult between the materials because some had different. It seems we have a fire alarm here, and I suppose we'll have to take a small break.
Yeah, we
Okay.
take a break. Sorry for that.
Petri, you will call us back.
Yes.
Okay.
Sorry.
Okay. So Chris, we don't need to run. Guys need. I've never seen this.
I think I'm going to get myself a cup of tea.
Yeah. Okay, let's come back. I think there is a routine. They can't just come back even though if it's a false alarm. It'll take some time. So
Yeah,
let's see. I'm not in a hurry, so
Yeah, so how am I going?
I think this goes beautiful. I mean I think it's let's not make it too relaxed, but well I haven't seen any difficulties with Jarkko so far, so we need to test him a little bit.
Yeah, well, I have a few questions about that last subject. I'm going to make myself a cup of tea.
Okay,
I'll be fine.
see you soon.
Oh boy.
We are alive. You're muted, Jari.
Well, that was a good exercise.
It's good to have. It was probably the thermal spray lab downstairs.
Well, you can build always a new one.
Exactly.
Okay, I think we can continue now.
Okay. Good to go.
Shall I get the ball rolling again?
Yes, please.
So I'm referring to page 74, figure 6.1. So something which was, I think, worthy of discussion is the orientation of these impacts with regards to the coating.
Mm-hmm.
So first of all, I need to check my assumption. I'm assuming that these impacts were on the surface.
Yes.
Okay. If they were on the edge for a thick coating,
mm-hmm.
How do you think the data in figure, the one that you just showed,
Yeah.
figure 6.3 would change?
If they're on the edge of a thick
Yeah.
coating. So edge
Analyze
of
the topic
sample.
behavior.
For a thick coating, we would have a lot less tolerance for this. I'd say there would be some chipping off of the coating. Or did I understand correctly? You meant the edge of the sample. Yeah.
So rather than testing on the surface, rather than testing on the lamellae this way, you're testing on the, rather than testing like that, you're testing like that on the edge.
Horizontally on the cross
section.
Cross section.
Well, that's an interesting one. It would certainly remove the substrate influence.
Yes.
The cracks wouldn't, potential cracks going downwards wouldn't stop. They could propagate till infinity. But otherwise, there would be mostly a lot of cracks on between the lamella. So on that horizontal direction, at least more than in the vertical one.
So would it require less or more energy on this vertical axis? So for the first data point, APS alumina, 0.6 to 1.1, would we be having less or more energy? Would there be more microcracks or less microcracks?
I would say there's more and less energy required. Somehow, since if we have the lamella like this and would turn it around and would be pushing in between, it's easier to open.
Okay. So if my understanding is correct, the impact energy is almost like a fracture toughness.
In a sense, yes, but it's more how to say, well, first it's repetitive, so with up to 1,000 repetitions, and with the spherical indenter, which makes the big difference that it's not meant to cause a crack.
Okay,
So,
let's just assume that it might be an accumulative fracture toughness. Are we talking about mode 1 or mode 2? Are we talking about a tensile or a shear with regards to the crack propagation direction?
Okay, now you've posed a good one. Regards to the direction, I would say it's most likely a mixture, but that's an easy answer. So maybe I would say tensile.
So that's for the data on figure 6.3. Now for the imaginary data, for the cross section, is it still going to be mode 1 or mode 2? Is it going to be tensile or shear?
I still want to say tensile.
Yeah. I think that the discussion point is really that this is a good way, potentially a very good way, to decipher some of the mysteries of that exist for thermal spray coatings. Now, I have one final observation about figure 6.1. So bear with me, this is a really weird one, right? So bear with me. When I look at these, I'm looking at craters on the moon, right? Now, here's the point. So here's an observation. Is there a self-similarity? Is there a fractal concept here with regards to scales about, you know, really macro, as in the moon, and all the seas which are formed in the moon, and really micro with regards to this test? What are your thoughts about that, Jarkko? The point is self-similarity of fracture mechanisms on something which is truly macroscopic and something which is probably 7 decades smaller. Do you know much about fractal dimensions?
Not that much.
Can you talk about self-similarity and whether there is an analogy here with regards to a macroscopic behavior? And it could be cavitation erosion, for example, a macroscopic behavior in industry. And I just used the moon as a very, very large scale one. And I invite Jari to jump in with any clarifying comments about that discussion point.
Well, I want to say there is a similarity in that it's the scale of the microstructure and the size of the indenter, and their relation is the deciding factor, more or less. In the moon, I'm not sure of the scale of microstructure in the larger sense, but it's more of a bulk material maybe. And here the indenter is still 2 millimeters wide. So we're talking quite big compared to these coatings made of splats that are 50 micrometers or such. So it's a macroscopic test for this microscopic coating. And for cavitation, well, that I want to say changes because the cavitating bubbles themselves are 10 micrometers, around maybe 20, which is the size of the splat. So that would be a different.
Okay, I'm just going down a thought process, by the way, so that, well, and that's the intention of I think this dialogue, to bring out potentially interesting features which might be helpful later on. I'll turn the chair back to Jari.
Okay, thanks. I still, as I said, I see that this experiment was the most successful I would say, in terms of development and all that. But I go to the development part. How would you develop this experiment? You would have this extra resources to go for this experiment.
Yeah, to make it better for research use, it would need to be, well, as such, I think I mentioned it there, that I think it would be good for quality control of this type of damage tolerant behavior. If you always make the same coding with the same process and you know its behavior in the test, it would be really fast for this type of use. But for characterization, it would still need some instrumentation. I would want to say the velocity control and measurement of the impacting head would be key. And to be really able to control the energy, so possibly have a loop back that you can input the energy you want and the machine does it for you and keep the energy stable. But to start, would just be repetitions of the same materials and trying out the limits of the machine a bit.
What did you think of ever? See, this is a method where you need to make the impact, but then you have to characterize. You have to. I think you mentioned that it's not straightforward to actually measure the volume of the material loss. You might weigh or use profilometer, but it's maybe you could avoid that by measuring the energy input to the damage. Or I don't know if you could even use acoustic emission in this case, but
there is I'm not sure did I mention it there, but in the machine there was a load sensor under the sample, and we could see some correlation, a change in the amount of load transmitted to the bottom of the sample when there was damage, especially in the case of these HVOF chromia, where it's clearly damaged. You can see the load isn't transferred as well. So maybe something could be done with this to play more in real time with the test. No need to go for a profilometer after, but you could see from the load that now this.
Definitely. Yeah. If I may, I would still go then further. The impact test. In figure 6.4, what's the direction of the impact?
In A and B, it comes from the bottom. In all of them, it comes from bottom up, but its angle is 15 degrees in A and B and 30 in C and D.
Okay, so the projectile comes from the bottom and then reflects back to the top.
Yeah.
Okay. That could have been indicated in the image.
That's true.
I actually guessed the other way around. Right. There's a number of, in the paper you have, there's in publication 3, there's much more on the cross sections and the profile of those cracks. I think we don't have them here, do we? I just want to make sure. Oh, we do actually, yeah. yeah, if we go to 6.8, and so what differences can, I mean, this is probably just an example of some of the investigations, but the coating is delaminated in both cases. And what can you say about the cracks and defects that you see here? They seem to be quite catastrophic.
Yes, yes, indeed. So here it was a bit of a naivety in the beginning to not consider that this test obviously goes to the substrate. As you see, the substrate is deformed. And if we would be successful finding a damage-tolerant ceramic coating or making one, it would have a coating that is reasonably intact after all this. But so what can I see here? Basically, with the thicker coating, the stress, I want to say theoretically that the Hertzian stress concentration depth is within the coating, and that's why we see so much cracking inside the coating, whereas with the thinner one, it goes over and it's actually thin enough to stay in one piece, if that makes sense.
Yes, that's yeah. In sorry, in publication 3, you have also another image. This figure 7. If you can jump to paper 3.
I will come there. Yes. So
indeed, the coating is about 3 times thicker. The chromium oxide compared to the TiO2. So wouldn't it be very difficult to compare these two materials when you have such difference in the thickness of the coating?
Yes, and I try to steer away from direct comparison because of that. We in fact, of course, did the cross section afterwards and saw that it had gone so thin in the preparation for the test.
Okay.
So at first glance after the test with the profilometer, you do these before you break the crater. Okay. You see different behavior and then you cut it open and you realize that it's thinner. So I tried to see what's the good and the bad with each coating individually.
So these coatings were vacuum impregnated before you cut them?
Yes.
The other thing which I find interesting is that there's no benchmarking with regards to classical materials. In other words, uncoated materials. How would you address that type of comment?
Well, that would be, especially knowing now what I know of this test, with the idea of adding the ceramic coating would not be to increase the ballistic protection of the steel. So we wouldn't be considering the properties of the substrate material that much. It's more in a characterization of the coating.
Okay, thank you. So you're saying that benchmarking is not warranted in this case?
At least with these materials, you would not want to protect or consider protecting a steel with the thermal spray ceramic coating against a bullet.
What happens if you had a bond coat?
That would most likely move the weak link to be between the bond coat and the ceramic, but there would be better adherence for sure. Delamination, possibly not, or a lot less.
So the real question is, for rather than just thinking about the damage tolerance of the ceramic by itself, you've already proposed that you might be able to change the crack network within the ceramic. You've already proposed that you might be able to have some sort of composite coating. You call them spheres to blunt cracks. How about a strategy of having a bond coat that is ductile, or a subcoat, let's just call it the subcoat, that is ductile and that can act as a sponge to improve the damage tolerance of the overlay? What are your thoughts about that?
Oh, that's a valid thought. As my thought process has evolved during the thesis as well, it is more about the system itself, and you can definitely, different bond coats have a different effect. So this would be it would be a like you said, energy sponge of the cracks.
Okay, thank you.
Okay, if we go back to the original run, maybe we were on 78, page 78. I mean, yeah. Now, I think this was very interesting. After that, we have this this Raman experiment. So you apply Raman and measure the stress of the coating, and the reference is the scratch residue particles. Am I right?
Yes.
So you do a erosion of the surface or wear of the surface, and then you monitor the particles. That would be zero residual stress reference, and then the coating would be then the compared. So I think it's a good, excellent tool, but you didn't have time to add that into your publication, I guess.
No, it was in fact, it was a micro impact fatigue test that was used for this, and it was expertise of the team in Belfort. So I had returned to Finland and I received the results later after publication, but I was able to add them to this, luckily.
Yeah. Okay, one thing a little bit. I'm not 100% sure. I haven't looked at it previously, but to me it sounds like one should expect that when there is a compression, you should go to higher wave number, and when you have tension, you go to lower wave number. So in this table 6.1, it looks like the opposite.
Yes.
So you might want to check that once more. And if you look at the reference 183, that's what actually to me occurs. So when you have a compressed state, you actually have higher shift in the vibration phases. So the excitation should be higher. And but so it could be that there is just little, but the result is still quite understandable. I'm convinced that this is the way to actually measure the coatings stresses.
In fact, looking at figure 6.5, that's what happens for the plasma sprayed coating. The dotted line is shifted to a lower number, meaning you are right.
Yeah, going to the higher number.
Yeah,
that could be just some misunderstanding of the results, but I'm still convinced that this is a powerful method and good indication.
Yeah,
I think it only shows that this is the value for for peer-reviewed articles, because when you submit that, it goes through a careful investigation, and there are so many places where you can check it, but this is a little bit risky to put original stuff here.
Yeah.
But I might be also wrong, but that's anyway. Might check that.
Good point to check.
Chris, do you want to continue, or?
I want to look at figure 6.7.
Yeah, that's an interesting one.
And what does it mean?
I had identical question myself.
Yeah. Another way of trying to quantify difficult results of the acoustic emission in this case. What it means is, after the fast Fourier transformation, we get the amplitude of different frequencies that we hear in during the test. And because it's a continuous line, I wanted to bin them somehow. Like here is first it's 50 kilohertz, that we have this many between 0 and 50, this many between 50 and 100, to get to the severity of the individual cracks. I admit it was a bit of a, to start, it was a bit of a question mark, what will come out of it. But then I did see some trends, and so my hypothesis is that higher frequency of the crack means basically higher crack velocity, so a more, how to say, severe crack, and lower frequencies could be micro cracking or crack deflecting a lot, and the higher would then be basically a major crack straight through. Did it
So let's look at the frequencies of, say, the bins from 200 to 225.
Yes.
So those bins, that bin is filled, is populated across the entire test.
Yes. If I'm not. Yeah.
Does that worry you?
No, not so much.
No, so what I'm trying to say, hopefully I can be a little bit more clearer now, is that within that bin is filled across the entire test.
Mm-hmm.
That means that you've got a certain type of crack being generated across the entire test. That means that there's no initiation point for a macro crack, for example.
No, I believe these cracks could all come at one point during the bending test, but their cumulative amplitude is high enough to put them high in this chart. So in the beginning, there might not be any of this frequency, nor in the end, there is one point where there's a lot, but this is just this graph is of all duration.
So do you know that, or are you just speculating?
I want to say I know it, because in the beginning of the test, there is no sound at all. The AE graph itself is 0, and then it later starts.
So just to, if this is being presented to a manager where they just want to know a number, what is good and what is bad? If I look at the APS fused and crushed, or APS agglomerated and sintered, HVOF, F&C, HVOF, A and S, which one of those materials is good?
In practice, you would want to have a low number in average all around would mean the least amount of cracking. It's just basing on this graph. But of course, it's a different thing if you have.
And does your graph show that for something that we already know, like HVOF, agglomerated and sintered might be the best coating?
No, it's not too clear from this, but it's not meant to be a clear cut which is best, because for that I have the other graphs for the flexural strength that I believe is the important part, that when does the crack occur.
Yeah. This is very, very interesting, and I congratulate you on taking the plunge.
I must add, it was not my specialty and quite interesting to learn about this, and especially learn that it's not easy. There's a lot of room for mistake, and I'm not saying I did some, but there probably a signal, how to say, someone experienced in signal processing would find maybe some holes or improvements to do.
Thank you.
All right. It's probably a powerful tool, but let's go forward to the 6.3. We have cavitation there. So was it so that the surface was not polished before the testing, which would probably make quite a difference?
In the beginning of my doctoral researcher's career, I did polish them based on convention from metallic materials, but I did find that for the ceramics there is very small, basically none at all, incubation period, but the damage is quite linear. So because it starts cracking right away, you get these initiation sites, there's no deformation. So then the test is quite laborious, and I decided that I can skip this part and get equally representative results.
Yeah, okay.
In any case, to calculate the cavitation erosion resistance, we use data points from the end of the test to eliminate any incubation. In all materials we have been doing that type of analysis.
So it was by weighing.
Yeah.
Yeah. I think this is a nice result, this table 6.2, that you do get clear differences, and however you seem to have HVOF quite superior in this. The same types of results you also get for the micro impact, or how do you compare this, let's say, excellence in cavitation to the other results? Is there any unexpected, or are they similar?
Well, in the case of cavitation, I believe it comes to scale, because the splats are smaller than with plasma spraying. They essentially are the same size or slightly larger than the cavitating bubbles. And if there is some splats that are detached, it's a small splat that leaves a small dent. That's not a big incubation site. Whereas with the plasma coatings, you have big splats that are well adhered because they're well molten. And the cavitation kind of drills one piece around and it becomes a site for a new, the next bubble. So there was a big difference between them here. Whereas in the micro impact fatigue test, I want to say it's more about the compressive stresses, for example, and the density hardness, more macroscopic properties.
Please remind me of the number of hardness tests that you did to get those standard deviations.
10 tests.
And why did you choose 10? On what basis did you choose 10? Sorry?
By convention. It's been kind of a standardized test to do 10 repetitions. Now, I know standard deviation from 10, it's a bit of a stretch still, but it's better than 5, for example.
But 20 is better than 10 as well.
And 30 is even better.
So how does one go about choosing the correct number?
You need to find a high enough number to have confidence and weigh that against the time spent, and also take the deviation with a grain of salt. You always remember, I have seen some places a hardness number of, for example, exactly 813 with no deviation. Perhaps it was made with 1 or more indentations, but this, in any case, you know that it's plus minus 100. You take them kind of as relative values.
I'm just wondering whether you've heard of Monte Carlo techniques.
I'm not sure, but I have myself, I'm veered towards confidence intervals from standard deviations that take into account the number of repetitions, and the higher the repetition, the deviation of the confidence interval goes lower as well. So it's kind of a catch-all. You can do only 3 tests, but then prepare to have a high deviation. Yeah.
So I would agree with your statement that 10 is the convention. Mm-hmm. So that is actually good news. From the being a pedantic person, though, the deeper level might want to think about validating that 10 is in fact a reasonable number. Mm-hmm. But anyway, that's sort of an editorial comment from me, and please don't take that as a severe criticism. It's an editorial comment.
Mm-hmm. That's good. I'm curious how many repetitions do you use, or have
my students do 100. Okay. And then they do a Monte Carlo simulation, and they figure out that the ideal number is about 10.
Perfect.
So there's no argument.
Okay. But you need to be professor first before you can do that. I still want to attack the issue of hardness and something in paper 1. You have this comparison. Well, I guess it's porosity, but it's in the same figure 8 in publication 1. You also, I think there is a
8. Yes. Here.
So is there there is a notion that there is always a better both spray methods show that the coatings are more porous when they are FC materials, as opposed to AS. Fused and crushed and this agglomerated, or what was it? But if you look at the image, the number number 8, I would say that they are identical, taking into the deviation of those measurements.
Yeah, they do fall within the deviation, but it's a propensity to find conclusions, I guess. Yeah. Based on these deviations and averages, it's likely that this would be the case if you would continue testing more and getting the deviation low.
Exactly.
But from this, yeah, it's a small stretch.
Yeah, but not that much significance. Okay, then if we proceed with this original introduction part to the chapter 6.4, the hybrid method. So indeed, in figure 6.11, you see this agglomerate, these like pockets of powder inside.
Mm-hmm.
Is there any way of avoiding that?
It's good question. It's hard to say since the porosity comes from the microscopic features of the coating, so that will likely be there. But to fill them with not powder but melted nanoparticles would be the key. And I guess, well, I still want to say it could be done by process parameter optimization further. But yeah, I'm an optimist that it could be done.
Yeah, how would you approach that?
Well, in our case with the HVOF, it's tough. The YSC or zirconia have such a high melting point that with HVOF, it's very tricky, at least with the current setup, maybe with a special version, but with the plasma, you could try to maybe increase temperature for sure, or maybe inject the solution in a different part of the plasma.
Okay. Where do you think this agglomeration takes place in the process?
Interesting. I'd say it's in the plume or the flame, because it's from a solution. It's likely quite well. We talked about isolated nanoparticles, but that are close, so they probably are formed inside still some liquid that kind of keeps them together in the flame, and then they have time to agglomerate. I have in mind an image I've seen in a publication, but it's keeping my mind, and I suppose it's speculation as well.
Do people measure the Zeta potential?
Of the solution?
Yes.
No.
Would the Zeta potential help you decipher whether there's agglomeration pre or post entry into the plasma or flame?
I can't see that. I recall Zeta potential used with suspensions to see the interactions of the particles in the suspension, but in a solution there's no particles until it's in the flame.
So my real question is, what are the physics behind the Zeta potential measurement?
Well, you had particles suspended in a suspension, and they have the debut length of basically their area of interaction within the suspension. And if there's another particle further away, they will stay separate. If they happen to approach so that they're, I'm not sure was it debut length, but the area of interaction, let's say, is close enough, they are immediately drawn together, and then their debut length is even higher. And if there's a third one that comes even there, and that will be.
So for a suspension, it may explain agglomeration.
Yeah.
Or, you know, electrostatic attraction, essentially. Whereas for a dispersoid, which is not a suspension, you are throwing doubt on whether these dispersoids would have the same molecular interaction.
Yeah, I've always presumed the solution to be homogeneous, perfectly dispersed, but of course it might be so that there is some local differences of the liquids, but I'm not.
Okay. Okay, thank you.
Yeah, I was thinking, are there any attempts to decorate the particles with these nanoparticles? I mean, the original particles, not to add them as a suspension, because I would think that you get these problems of evaporating the suspension, and avoiding agglomeration would be a very difficult task.
You say using traditional powders and add nanopowders
on top of it, decorated.
I guess it seems familiar that there could have been trials like this, but in practice it might be difficult for the powder to flow and to be sprayed. The sprayability might become an issue if there's a layer of nano dust on top. It gets stuck everywhere in the hoses.
Well, that's obviously it's something like that. If we want to proceed further, I would go to it. Actually, the results presented in paper 5. I think there's a nice optimum and incredible differences in the cross sections demonstrated in this paper 6, figure 6.12. So both, I think it's a good result. I don't have any critical comment on that. I would actually go to the conclusions, unless Chris, you have something you would want to still stay in the results and discussion part.
I think that I'll leave my comments or my discussion points that will become apparent when we talk about the next section, section 7, conclusions.
Yeah.
Let's move on.
Yeah, I think you very systematically draw these conclusions at both. Yeah. But there is no straightforward way to solve these issues. I think the threshold for coating damage was shown in this paper, that you could actually evaluate that, and it could be used as a measure method. And that you summarize it, there is no there is no one method of measuring the system's property as damage tolerance. But that the impact, micro impact fatigue would be most, let's say, effective. I would very much agree with that based on this evidence.
So what I would ask Jarkko for is one bullet or two bullets or three bullets. You're going to think I'm very lazy, right? But with regards to the conclusions, what would be the executive summary?
Well, to sum it up.
Very, very briefly, what would be the so-called elevator summary?
Yeah.
Well, damage tolerance is very application focused. So the test method should be close to reality to avoid many presumptions on the way. Therefore, the micro-impact fatigue is most suitable currently for its measurement. That would be one, and one subpoint, and the third one. And of the side of the coding development, work needs to be done, but suspensions are close.
Okay, let me ask a very blunt question. Is thermal spray the way to go?
For ceramic damage tolerant coatings, yes. Yes.
Okay, but then there are various disclaimers, which is fine with regards to application, with regards to environment, with regards to whatever.
Other requirements.
But generally, thermal spray coatings show attributes as damage tolerant materials.
Ceramic, they show potential. The current developments compared to what it used to be, it shows it could be heading that way.
Okay, let me go down a slightly different track. Let's just assume that they are no good. Just assume they're no good. Can you think of an instance where, even though they may not be as good as another material, can you think of an instance where they could be or should be applied, even though they may not be the best material?
Yes, for sure. You're not specifying any applications now, so I can say, for example, the manual application of coatings. There's many other, say, thin film technologies that could be better coatings by property, but just for a specific application, if you need to coat only a part of a large component, that would be a reason to go with a lesser quality coating that's just in practice easier.
Or it could be for remanufacturing.
Yes, for example, yes.
So you've got a component which costs $100,000. It costs you $5,000 to remanufacture it. So you remanufacture it with a coating, and you know that it's going to last for X months, not X years. But you're happy because you're still making money.
Yeah.
Okay. I don't know whether I can ask one of my strange questions, Jari.
Yeah, I don't either. Maybe, yeah. I have a similar type of approach to go when we go to the future visions 7.2. Often in this type of, and I think here as well, it ends up into a very extensive list of wishes. That we should do this, we should do that, and of course we should do this and that. So Could you, I don't know how to formulate this question, but if you would take some important application of these thermally sprayed coatings where you really need damage tolerance, I don't know if it's a landing gear for airplane or whether it's a paper machine roll, what would be in and what order, how would you approach in the development of the process, the coating itself? Would you start from a process, powder, different gun, and or what? Like 2 or 3 in the order of most significant ones into what you conclude based on your experiences here.
But if I must, I would want to say that they are a combination, the powder and gun. You cannot choose one and then go for the other, but they work together. Mm-hmm. But most significantly, I've now seen the feedstock, because that's the basis of the whole coating process. If you have poor feedstock, it's hard to make a good coating with a good process. And for damage-tolerant coatings, what I would want to try next would be to go with the suspension route with the current optimizations. Maybe try to optimize more, if not even with these, and see these other tests like the micro-impact fatigue with the suspension sprayed chromium oxide. For example, this suspension chromium oxide we had, it was easier to spray than a powder chromium oxide. It required less heat, it deposited better, faster. It seemed, I would be interested in trying that as the low-hanging fruit currently. Then this hybrid thing is interesting to try, but there is a lot more variables and still question marks, obstacles. But that would be suspension, stick with HVOF and do these other tests and see maybe then a larger component later on.
Okay. Yes. Chris, do you have something?
I agree with your comments that the future work is really like a shopping list, and that's okay. That's quite normal and traditional. What I would like to ask is something a little bit more deeper, and this is for Jarkko. Knowing what you know now, what would have you done differently with regards to your PhD studies? So what I'm asking you to do, I'm asking you to give some advice to those people who are going to follow you from the heart.
Yeah. Spend time planning, discussing with people, with high-level researchers about your ideas to find the good way to go. I was a bit excited to jump right in and start doing codings and testing them with the first idea that comes up. And later, like you said, the shopping list comes from having done a variety of things, which is, it's nice, it's fresh. But in terms of the totality of the work, it would have been better to start a bit slower and then go with intent and thinking of different scenarios before you actually start doing. That would be my.
So you've covered many areas. You've covered powder processing, feedstocks, thermal spray processing. You've covered mechanical testing. You've covered microstructural analysis. Which area do you consider yourself, let's not say expert, but which area do you feel, which of those areas do you feel most comfortable with?
I do feel it would be I feel quite well versed in most all of them, but maybe the testing part is something that I've, because of developing new tests and thinking about a new kind of thing to measure, I've had to think not only these tests, but the alternatives and see the mechanics behind. So in those, I guess I have quite a good understanding of when a new test pops up, what to look into. Is it any good on this part? Is it any good on this part?
Let me rephrase the question a slightly different way. What area would you feel you would need to develop further in this area, in this wonderful, huge universal area called thermal spray?
I would want to look more into the process, the spray process, and its intricacies. I used many processes, and I know them somewhat, but still superficially. But to really know the physics of a plasma spray would be very useful.
Okay, I think that I've asked my strange question, so thank you for allowing me to do that.
Yeah, I think so have I. So I guess it's about the time for the statement. So the field of this dissertation is very important in practice of engineering surfaces with high relevance in engineering within the process and energy industries. Thermally sprayed coatings are state-of-the-art engineering solution that is essential to provide high-performance surfaces for process engineering components. The combined need for high wear resistance and chemical stability demands ceramic coatings. The critical issue is how to manage the brittleness of the coatings that may potentially result in sudden and catastrophic damage. The development of reliable thermally sprayed coatings requires both coating process development and mechanical characterization methods. This is the exact topic that this thesis encompasses with such ambitions and objectives stated. The dissertation is composed of an introductory part and 5 original publications where the candidate is the first author in all of them. The introduction contains an extensive literature review on the specific topics of several thermally sprayed oxide coatings, the various strategies to enhance the damage tolerance are introduced, elucidating the recent achievements reported in literature. Finally, the most relevant characterization methods are critically assessed. Then the methods and materials are presented following the results, discussion, and conclusions. The scientific maturity of the candidate is well noticeable in the critical chapter of scientific contribution. It is well concluded that there is no one single characterization method nor one thermal spray coating solving the problem. The most novel results have been obtained by obtaining a micro-impact fatigue tests. The excellent pioneering work has been carried out in development of suspension plasma processes. The successful optimization of SHVOF coating combined with auxiliary air nozzles and air curtain resulted into excellent cavitation resistance of the coating. The candidate has a substantial contribution to all publications and the results. The content of the work is logic and consistent. The work has produced new information on the understanding and development of damage-tolerant ceramic coatings. The work is addressing in a coherent manner the well-specified but broad problem area. The dissertation contains scientific findings that are excellent in terms of novelty value. In addition, the work has an important practical value for industrial companies active in the area. The work follows good scientific practice. The doctoral dissertation should be a specific investigation that provides a comprehensive insight into phenomena and mechanisms in the area of the subject. This work shows that the candidate has pertinent knowledge in the field and can use scientific research methods. The thesis and the discussion at the examination demonstrated that the candidate has excellent knowledge in thermally sprayed oxide coatings, their characterization, and potential for successful damage tolerance. The candidate defended his dissertation in public, giving objective replies and showing pertinent knowledge. In summary, taking into account the merits of the work, we consider the dissertation to fulfill the requirements stated for a doctoral thesis, and we recommend it to be accepted with a grade approved with distinction.
I now respectfully invite any members of the learned audience who wish to offer criticism of my dissertation to request the Custos for permission to speak.
Koska lisäkysymyksiä ei ole esitetty, väitöstilaisuus on päättynyt. Since no further questions have been presented, I declare public examination closed.